interested in how does stellar mass get built up in the universe. So if you go out and plot how massive are all the different galaxies out there, you do it over cosmic time, and you'll look at this as redshift going this way, so this is getting further back in time, and then we're talking about stellar mass going up in the y-axis, and these objects are obviously growing much more massive over time. We're also really interested in star formation density. These both come from the same paper. Again, redshift, we're going in look-back time, and then this is more star formation. And we see this trend here where there's this hump at about cosmic noon, and then it goes back down. And so I'm interested in understanding how does merging fit into this picture of these evolutionary changes in mass and star formation. There is also a slightly more complicated picture. Don't start going crazy with this. I'm going to walk you through it. That the picture of evolution becomes a little bit more complicated if we start with things like high Z disks and we say, okay, we know we can crash galaxies together and we can make them change, but are there other ways besides crashing them together that might cause these morphological changes? So we can start with a high redshift disk, and we have two different modes that we could possibly go into. This slow mode right here, where gas is falling on to these objects, I think, if I totally understand this, and then getting to, at today's time, red spheroids. Or we could also have the sort of gas compaction story where they become star forming and compact, and then they end up getting quenched and becoming still compact, but less star formation, and then moving on this picture. And so we don't really understand how merging fits into this total way that galaxies might be evolving over cosmic time. So what did we do? We visually classified model subtractive residuals that, as Dan pointed out, were provided to us essentially by a researcher named Arwin Vandervelde and his collaboration team. And what they did was they took the entire sample of 50,000 candles galaxies, they extracted all of the sources in them, and then they ran all of those sources through a program called GALFIT. So right here we have the H-band image, that this is an image that would have been run through GALFIT. GALFIT would have created a model for these objects based on what sources it thought were there, and then subtracted that model from the original image and leaving a residual. And so this is a pretty good example of a residual that has some interesting stuff going on with possible interaction, tidal features. We're interested in finding the things that look like this. At least I. Oh, what's mine? Oh, no problem. No problem. So the specific residuals that we looked at came from the candle sample, and they are massive, high redshift candles data. So these are the different fields that they came from. It's really not that important, but there are 5 premier fields. And the reason that we like these fields is because they're also matched up with a lot of other multi-wavelength data, like radio data, X-ray data, infrared data, and stuff like that. So we're hoping that these objects we can combine with other multi-wavelength stuff to really get a good picture of what the physical nature of these features is. And then these are the specific sample details. They were H-band images, large stellar masses, high redshift, and H-band magnitudes less than or equal to 24.5. So another story or component to this is we showed this plot. Don't worry about, basically ignore all of this slide. I just didn't want to make it work. But we showed this plot at the AAS during a poster session. And a professor named Jillian Scudder came by and asked me, see, you can't read these. These are plotting plausible mergers and interactions. And what she asked me was on this plot where we have stellar mass, larger stellar masses going this way and more star formation going up, she asked, why do we have potential mergers and interactions going on in this quenched population? We have a star-forming population right here, and we have a quenched population right there. And it doesn't really make any sense when you go back to that first image that I showed that we associate mergers with star formation. So why are these here? And honestly, my answer was, it's possible we made a mistake, and I hope that's not true, but these could be errors. And so I went back and looked at them. This is the exact same plot as I showed you before with the same, you can hopefully see them better. These are the same objects that are plotted, but this is in a UVJ space. So this is from Z1 to 2, and this is getting redder, and here is the non-star forming population, and here is the star forming population. And you can see that when we plot it in UVJ space, we do still have lots of these morphologically disturbed, either because they had an irregular center or because they had a plausible double nucleus. We could see tidal features, things like that, that are definitely in this quenched or non-star forming population. This is just zooming in on what I showed you just a second ago, zooming in on the so-called Williams wedge. So these are all the quenched things, and you can see we've got some plausible tidal tails and things like that. So here, oh yes, and this is the same thing, but just for Z from 2 to 3. So you can see there are far fewer tidal features and things like that, and they seem to be bunched in the star forming area. So going up and pulling up pictures, and I have to caution you, these are cherry-picked images. Like I have picked out the ones that I thought were sort of particularly cool. But I went and pulled up, like, are these mistakes or did they actually show something neat? And it turns out they actually did show some pretty neat stuff. So here you can see we've got this sort of spiralish, tidal-ish looking thing, although there's no companion here. Here we have 2 awesome companions with, you can't see it super well, but these are definite tidal features that are coming around. And in fact, Kameshwara, one of my compatriots, will probably talk about this tomorrow. We have some, again, low surface brightness, but sort of disturbed looking features there, disturbed looking features there. So we didn't totally make a mistake. These objects actually turned out to be somewhat interesting. Here are a few more. Just wanted to showcase we found double nuclear objects that appear, plausibly, to be super clear about that, plausibly had some sort of double nucleus going on. We had another one, again, sort of hard to see, but you can see these are very asymmetric residuals. They have companions with them. They look sort of tidalish, and they're in the quenched star-forming population, in the Williams wedge of UVJ space, the non-star formers. This was one of my favorites, so I just wanted to show it. This was at Z 1.9, and this looks like a grand spiral, maybe some sort of interaction going on. Again, non-star forming. So this is to show you real quick. These are more of the flags. I know this is a total mess. I'm going to zoom in on it in a second. But these are just more of the sorts of asymmetric or high surface brightness residuals that we had, like spirals, plausible clumps, sort of miscellaneous and all of that. And that's sort of where they fall. And I'll zoom in again on the non-star forming population. These are all of the sorts of irregular, asymmetric, high surface brightness objects that we found that I wouldn't necessarily expect to find in the non-star forming population. So finally, what do I want to do from here? So Kameshwara, I want to go ahead and plug his talk. Kameshwara is one of our PhD students who's going to talk tomorrow and give a talk about extracting tidal features. We had the question that was asked earlier about, okay, so you see these tidal features, where do you sort of go from there? One of the things that would be nice is if we could have a rigorous way of identifying tidal features and then quantifying what the sort of physical properties are, or not physical properties, but quantifying the flux throughout these spaces. So again, you'll hear more about this, but we have a method by which we can take a residual like this, or an image or something, but we would do this on residuals, run it through a software pipeline that would say, these are your tidal features. And then we could start to ask questions about how do these features, how do colors change along these features? Do they all have similar shapes? Do they have similar sizes? Different things like that. We could actually start to understand some of their physical properties. And we would do this not just for the star, or not just for these tidal features, but also for some of the things that we showed, like spirals and clumps and double nuclei and all kinds of things that we could eventually, I guess, I don't know that they can extract clumps, but I'll just go ahead and say that. So yeah, so that's basically the next step is we've identified all of those things, and now we want to start looking for their different features. So thanks to everybody that I work with and everybody who puts up with all my stuff and fellow graduate students, Dan,